So let me introduce Professor Giovanni Geraci. He's associate professor at UPF University, and also he's senior research lead, senior principal research lead at Nokia. And today, some time ago, he came to Moscow, and we took this opportunity to invite him here to give a talk. And today he'll present his vision on AI and wireless digital twins. So, thank you.
So, good morning, everyone. It's really a pleasure, to be here. And I took the opportunity because I was visiting Moscow because my wife is Russian, so I traveled with her, and I reached out to Evgeny. I think we bumped into each other at some conferences, but never really got to interact. And I was really glad that he agreed on taking up this opportunity. So, I recently changed jobs a few months ago, and so for the last few months, I haven't really given many presentations. And also, I changed my topic, the things I'm working on. So when you invited me to give a talk, I was thinking, what should I talk about? And I decided to make a presentation on a topic I'm currently investigating, which is wireless digital twins. I will explain what I mean by wireless digital twins and the use of AI. And I wasn't really sure about the title, whether it should be AI for digital twins or the other way around. So I chose AI and wireless digital twins because there's kind of some interactions and intersections. So this is the first time I give this presentation, so any feedback is absolutely welcome. And please raise your hand anytime, because as I said, I don't have to go through all the slides. We can just focus on whatever is more interesting for you. This is the outline. So first, I would like to say what a wireless digital twin is, at least for this presentation. And in particular, we will see that there could be different definitions of wireless digital twins, and I'm going to focus on a site-specific digital twin. I will explain what that is, okay? Then there's two more main parts. The first one is how do we create one? And I'm going to mention two ways. One is via ray tracing, and the other one is using generative AI tools. Okay, so this is how we create a digital twin in the first place. And the second part is what do we use it for? So applications of a wireless digital twin, and I'm going to touch on two main applications. One is for simulations, which I think might be interesting also for some of you. And the other one is for machine learning model training, because we need data for model training. So I will say, why wireless digital twin helps. So this is a definition of a digital twin taken from Wikipedia. So long story short, a digital twin is a digital copy, a digital model of a physical system, right? And this has been used in many major industries already, in automotive, aviation, healthcare, finance, etc. But what about networks? So it's an emerging concept, but still, it's still developing. So I'm going to focus on the RAN digital twin, the radio access network digital twin, so digital twin of the wireless network. But still, this is quite generic because the radio access network is made of many different pieces when we model it. For example, we have the model of the traffic and the application that sits on top of it, right? We have the model of the network, the networking, the protocols, all these things. Maybe some of you are focusing on that. We have the model of the radio, right? The physical layer. And we also have the model of the environment, because the radio interacts inevitably with the environment, right? We're sending electromagnetic waves. So the focus today for me is this box here, okay? So I'm going to talk about the radio, the wireless digital twin. So the focus is on the 3D model of the environment and how the transmitters, the receivers, they interact with this. So we can model the physical layer. Okay, that doesn't mean that there aren't digital twins for the other parts. There are, obviously. I'm just going to zoom in on this because that's my expertise in any case. Okay, so what we need is to somehow capture the physical reality of the wireless environment. That is very difficult, and we will see to what extent we can do it and how. So there are many challenges. No need to go through all the bullets, but I think the first one is that there isn't really a single definition of a wireless digital twin. It's not really clear what that means. It's hard to collect data. It's hard to calibrate a digital twin. It's because it's really hard to model the physics accurately. And so it's also ambitious to achieve a near deterministic digital twin. We will see what that means, the difference between deterministic modeling and statistical modeling, okay? Also synchronization challenges if we want to update this in a close to real time. So, but the good news is that there are also some new enablers that make people think that this digital twin might actually happen. And here I'm listing 4 main categories. First is there are more and more 3D maps available for other reasons, because there are other applications, AR, XR, so extended reality, for autonomous driving, for the metaverse. So there are more and more even open source available maps, okay? Also sensing is coming up. There are more and more sensors deployed at the network side, at the user side. If you know about 6G, one of the main use cases is sensing, not just communication. Probably you've heard about joint communication and sensing. So this sensing can augment the information from the maps in a way, LiDAR, all those things. Ray tracing has been improving. Traditional ray tracing is computationally very expensive, but as I will mention, there are new GPU accelerated ray tracers that are actually much faster. And also generative AI or AI in general can help us improve over those things. If I have to summarize in a sentence, we use the information that is available and we can learn what is hard to measure through AI, okay? So to make a model that is good enough for us, basically by having also updates from the physical system into our virtual model. So the bottom line is that maybe wireless digital twins can leverage these advances, and even though it's really hard to have a digital twin, but perhaps in the near future, we can make better and better models. So So because the definition is still blurry, I think at this point, I want to highlight these 7 dimensions. This is taken from a presentation from Jeff Andrews, adapted. I think he had 8, so I condensed 2 into 1. But basically, digital twin can be many things depending on these dimensions, in my opinion. What are they? So the accuracy of the object mapping. So we have maps, but what is the accuracy of these maps? Do we know them at the wavelength scale, say the objects, right? Or is it like tens of meters? So this is going to determine the kind of digital twin we have and what we can use it for. Yes, please.
May I ask a question?
Of course.
Could you please clarify? Is wireless digital twin in some sense an extension of channel models?
Yes, it's really related to channel modeling, of course. Yes, it's very much related to channel modeling in this case. Yeah. Even though it also depends on the radio part. It's basically a coupling between the radio, the transmitter, the receiver, and the electromagnetic environment. Yes. The properties of the objects, right? So that you need to model like reflection, absorption, everything that happens in the propagation, okay? And you can do it more or less accurately. There are some things that are really difficult to model, like the scattering, okay? The scale, do you want a digital twin for a single cell of the radio network, or do you want it for the whole city? That, of course, affects what you can do. The fidelity, right? So how accurate you want this model to be. Should it be deterministic or should it be stochastic? Okay. The sensing richness. So we said we will have more and more sensors. So depending on what we can incorporate, how much sensing we have and how often the sensing is performed, and how often we need to update this digital twin. Maybe full updates can be on the scale of weeks, let's say, but then for certain applications, we need every few milliseconds to update it. Let's say you want to do channel estimation real time with this digital twin. You need to update everything every few milliseconds. If a car passes, that's going to change your propagation, let's say at millimeter wave completely. There's a blockhead, etc. And the inference time, because of course, the larger we make it, the more complex we make it, the longer it takes maybe to run an iteration of this digital twin and have a measure. So that's going to affect what we can use it for, right? So how quickly can we run a test using digital twin? So obviously one cannot have everything. So I guess depending on the use case, one has to give precedence to one over another. And here there's these 4 levels that I wanted to highlight. It's adapted again from some other papers, but I gave it my own twist. So these are what I call the 4 levels of the digital twin. Level 1 is analytic twin. this is a mathematical modeling of the channel, right? So you were asking about channel modeling. Maybe we all know Rayleigh fading model, Rayleigh fading. Okay, so this is a good model that maybe when we started our PhD that was good, Evgeny, but now people want something that is a little bit more realistic. Then there's a statistical twin. This is more like the 3GPP model, okay, 38901 ITU models. So this is many companies took many measurements in many cities and they did some regression and we have the statistical model. This is what the 3GPP is using right now still, okay, in 2024. Good. And then this is the site-specific twin. So here I get to what I think is more interesting. So this is site-specific. So it's not statistical. This is I want a model for the neighborhood around this building. Okay, I don't want a model that's good on average on urban macro scenarios. Okay, site-specific. So for this, I need detailed maps. I need ray tracing or AI, as we will discuss in a bit, because what we want to do is to model site-specific channels. Okay. However, why is there a level 4? Why is level 4 better than level 3? Level 3 is what I define as offline. So this for me works offline. Maybe it's really accurate, but it works offline. Like I generate my channels, but I don't use it real time. If I want to use it real time, obviously it needs to be even more accurate and it needs to be updated real time. Okay, and accuracy obviously depends on calibration, and I'll mention briefly about calibration later. So today, I want to focus on level 3, okay, because I think there's more to discuss. Level 4, I've been seeing some interesting papers, but it's really, really ambitious. I think if we jump from level 2 to level 3, that's really great. Okay, so why do we need? So the focus now is on this site-specific twin. Okay, so why do we need site-specific twins? What are the use cases? So one key use case for me is machine learning model training. So I will mention today throughout the presentation a few use cases. There are maybe 3, 4, 5 use cases that 6G is considering, and even 5G for machine learning applications at the physical layer. One is when you use millimeter wave, you need to do this beam alignment, and this beam alignment takes time because you need to sweep your beams to align with the receiver. And so machine learning can help you basically doing this faster, predicting the beams that you should use. This reduces the overhead. So you can learn this through machine learning, but obviously this is a highly directional problem. So if you don't train your model with data from the scenario where you're going to deploy it, it's going to underperform, right? Because it's really specific. It really depends on the obstacles and the blockages, right? So you need site-specific data sets, but we all know that collecting data is expensive and hard, labor-intensive, time-consuming. So you might want to generate this data synthetically, and that's where the digital twin comes into the picture, okay? So for site-specific data generation. So to do this, what we need to do is we need to capture the radio propagation feature, and in this room, we all know what that is. We need to model the path loss, the multipath, the Doppler, blockages. So we need to account for the geometry and the interactions between, again, the radio and the environment. It's those two boxes that we had at the beginning of the presentation. And once again, I want to touch upon 2 approaches. One is the more traditional ray tracing, and the other one is maybe to use generative AI models to replace or to complement the ray tracing, okay? So requirements. So depending on what we use this digital twin for, we have different requirements. So an easier case is when you only want to model the large scale channel. So you want a coverage map. Example, there's an area of Moscow where maybe there's no coverage, and I want to deploy an additional base station to improve coverage. So I want maybe before I go and deploy, I pay for renting the site. I want to see how much predict the what if scenario. In this case, it's a large scale problem. You just want to know, receive power. You want basically reference signal, receive power, this kind of things. You don't need the full multipath. Okay, so this is an easier problem. You basically need heat maps for this. Maybe if you want to do mobility management, that's also good enough because mobility cell association is based on signal strength. It's not based on the full multipath. But for many other problems, especially at the physical layer, you need the small scale fading model. Okay, you need the full multipath response for channel estimation, for millimeter wave, for mime, or recording, all those things, for localization as well. Okay, so I'm going to focus a little bit more on this part because it's the more challenging one. As we said before, we might want to be real time or not. We're not going to discuss real time things today, okay? And this can be more or less accurate, obviously, and this depends on whether we can somehow calibrate the digital twin with real measurements, and we will discuss how and whether we can do this. Okay, so okay, so this picture. Don't be afraid of the complexity of this diagram, because first of all, I'm going to show it many times today, and for now, let's just focus on this part. Okay, then we'll talk about the rest. So for me, this box is the digital twin itself, okay? And I can create it in two ways, through ray tracing or through generative AI, okay? Later, we're gonna discuss about this. It's not as complex as it looks, okay? So this is the big picture for today. And first, I'm gonna talk a little bit about ray tracing for the digital twin. Probably things that you all know, but I want to share some recent findings about what's available, okay? So this is wireless digital twins via ray tracing. So this is one tool that has recently, being commercialized, and I haven't personally used this directly, but I have investigated it. It's the NVIDIA AODT. Okay, so this is it's actually called digital twin. Okay, so this is basically it's a system-level simulator that has everything. It has the ray tracer, the physical layer model, the full stack, and the system. Okay, and it's GPU accelerated. Okay. So if you only want the ray tracer, you can run this in EM only mode, and basically it gives you whatever a ray tracer gives you, which is for each link, all the paths and the channel impulse response and the channel frequency response. This has some drawbacks, this too, because you need to operate through a graphical user interface. You cannot have like a configuration script and you automatically launch many simulations and stuff. So if for some of you this is unclear or too easy because you already know this better than me, feel free to raise your hand and we can move on. But this is just one slide mentioning this tool because it's really important in the community. What maybe some of you know better is the Shiona ray tracing, right? So this is much more targeted for us as researchers, and I have used this directly, my students as well. So here's basically how you use this ray tracer, which is open source and Python and everything is open, okay? So you download maps, and it's very easy because there are basically maps for every city available on OpenStreetMap, so you can download maps. The building height I hear is not very accurate as much as the 2D dimension, but it can be corrected using some other data sets. Then you get this map, you generate a scene using this software called Blender, which is also open source, okay? And basically you go from these polygons onto some XML file. Basically you get meshes, and these meshes using Mitsuba are what you plug into your ray tracer, okay? So you import a scene with all the objects and everything, all the materials as a mesh, and then the ray tracer, once it has this scene, it can run. So basically, the ray tracer has objects. Each object has radio material properties. There's different properties, the permittivity, etc. Right? And then, of course, you need to specify where your transmitters and receivers are, and then you just run the ray tracer. Yes, please.
Yeah, so I quite, this is the picture I had in mind when you talked about the NVIDIA's previous model, and I just wanted to figure out what's the difference between this one and the previous one.
So easy answer is they are developed by different teams, and these things don't talk to each other. Easy answer. So therefore, these people are in the US, and these people are in Paris and in Germany. Okay. So this is more for research. This is really for people like us. Okay. And this one is more like it has a fancy interface. You can really see the beautiful rendering of the scenes. They also have a commercial version that they sell to telecom vendors and operators, etc. But it's also more computationally complex. It has a graphical user interface, which for some people in corporate might be nice, but not for us. What do we do with the GUI? We want to launch batches of simulations. So we want scripts, etc. I have much less expertise on this, and I know this better. So obviously today I'm going to talk more about this. This has other advantages that I will mention in the next slide. Okay. Also, of course, this also has advantages. Like, as I will say later, this is developed, as far as I'm aware, in CUDA. Okay, so this is CUDA code that runs very fast on GPUs, and this is TensorFlow. Okay, so this is Python code. Still, it's GPU accelerated, but it's really two different paradigms. Okay, what to mention here is that in Shiona you have two modes. One is the radio map solver. This gives you coverage. This gives you a heat map of the signal strength. Okay, it doesn't give you the full multipath response. So this runs relatively fast, but it doesn't give you the full fading. And the path solver instead runs really every single path, and it gives you all the info with a certain approximation. Okay, so we'll focus more on this one because that's what we need for the physical rate. Yes.
May I ask a question? Can this model be run on CPU instead of
Yes. It runs. It just runs slower. By runs. Yes.
by magnitude or?
Yes. By magnitudes. Yes. It can be run on CPU. Yeah. I'll talk a bit. I think I have a slide on the complexity of this. So one important thing I didn't say about Shiona ray tracing yet is that it's differentiable. Maybe some of you know this. What does that mean? Because it's implemented in TensorFlow. I don't want this to sound like an NVIDIA sales pitch. It's not, so don't worry. I'll talk about the things later. But because it's TensorFlow, everything is tensors multiplications. So it's differentiable. Differentiable means that you have some inputs. It could be even the position of the objects, the radio materials, the positions of this. These are inputs. You have some outputs. You can calculate the gradient of the output with respect to the input, which means if you have some loss function, you can adjust and optimize any of the inputs. It's fully differentiable. So you might wonder, why do I need that? One important reason is for calibration. Because imagine, let me go back to the diagram. Imagine that here you have modeled the properties of this building, okay? This generates a certain channel impulse response, and you have the ground truth because you measured. So based on the loss, on the difference, you can backpropagate the error and calibrate and tune this guy until they match, okay? So this is what they showcase. This is the folks that developed Shiona ray tracing, right? Jakob and the rest. So here, basically, they calibrate that. We're going to see the diagram, but that was not the purpose. You have different material properties, the epsilon, the mu, etc., the scattering coefficient. And by backpropagating the errors, you see how they converge to the real value after a few iterations. So you calibrate in the properties of the environment according to your measurements if you have these measurements. Okay. Now, how this is done? So yeah, it's done by computing. Say that you can calibrate on the channel impulse response, for example, to match the delay of the different paths, right, and to match the power. Okay. And so maybe you have some measurements. If you have some standard, you can use off-the-shelf material properties like concrete, etc., right? And then you have a certain mismatch, and then when they calibrate it, they show a much better match, okay? Notice one thing, that here, what they do is not, I have the real material and I want my material to be the same. No, I want my material to match the final output of the ray trace. Okay, it's different. It's different. They don't, their goal is not to match the real material. Their goal is to tune the material in the simulator so that the final channel generation matches the real one. It's two different concepts. Okay. And that's why they use this concept of the neural materials. Okay, I don't want to spend too much time on this, but this is an overview of Shiona, and you were asking about CPU, GPU. Okay, so this refers to the GPU, but in general, I made this table myself, and it might have errors. Okay, but I think overall it's correct. So these are the variables when you run the ray tracer. Okay, you have whatever batch size. how many users, how many antennas at the user, how many base stations, how many base antennas at the base station, OFDM symbols, number of subcarriers, number of paths. This is the complexity of the ray tracer. When should the ray tracer stop? You know, after how many, say, how many bounces, and then I stop, you know, propagating, etc. And whether you want to model the reflections, the diffusion, the refraction, etc. So there are three main things for me that are important. First, how long it takes to run the ray tracer, and second, how much memory it takes. So for GPU, that's very important. You're limited by the VRAM. And the VRAM comes into picture in two places, as far as I understand. One is when you compute the paths, because it saves all these paths as a huge tensor on memory. So depending on certain variables, this tensor gets bigger and bigger, okay? Depending on how many transmitters, receivers, how many paths, how many bounces, etc. This takes more space on memory. And the other one is when these paths are translated into the channel impulse response to get the OFDM channel grid, which is, you know, symbols by subcarriers. So this is another tensor, and basically the size of this tensor is affected by all these variables. This table is important, you know, when my students say, you know, I get out of memory, blah, 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 I'm like, you know, look at these things. It's very easy to calculate how to optimize your simulation so that it still fits in your GPU memory. Okay. Anyway, but they made it really fast. Okay. So now, one way is to use ray tracing. I discussed some tools that, in my opinion, are good for us as researchers. Another way is to use generative AI, and I want to mention this now. So we are still in this focus, okay? So can we develop this digital twin, or basically this channel model, using generative AI instead? So what's the idea here? Once again, traditionally, we use ray tracing. Why is that not good? Well, it's computationally expensive, okay? It's deterministic, which sometimes is not a good thing, because if you use this data for ML model training, you might overfit the data because they are deterministic. So an emerging solution is generative AI models. Okay, so for a few years now, we have a bunch of papers that use generative channel modeling. Okay. The properties we want from this is the usual. We want them to be site-specific models and spatially consistent, and also computationally light, so that maybe they're faster than ray tracing. Okay. What do we use them for? It's the same two applications that I have in mind. One is to generate channels to run simulations, and these would be faster than the ray tracing. And the other one is to create data, synthetic data, to train machine learning models. Okay, and I will expand a bit more on this. So this is a bit of a comparison of the three ways I see. One is stochastic channel models, like the 3GPP models. They are not site-specific. They are not physically consistent. They are stochastic. Ray tracing, they are site-specific. They are physically consistent depending on the accuracy of the model, but they are deterministic, so somehow they lack diversity if I want a lot of data augmentation, for those of you who know about machine learning. And then there's generative channel modeling that in theory ticks all of these boxes, okay? So basically the flow is like this. You model the environment, you feed this to a generative AI model, and this model gives the channel, okay? But of course, it's statistical, so it gives you a distribution of the channel. So this is like LLMs. Yes, please.
Can you clarify about the physically consistency? Because if we consider, for example, 3GPP models or Quadriga, if you know this one, they were calibrated, for example, using some real measurements from Hamburg or Berlin, some cities, and so these statistical properties of the channels are physically consistent. Or no?
It's a very good question. And to be honest, when I checked my slides yesterday, I wasn't sure whether this should be a tick or a cross. Okay, it depends on what we mean. So for me, physically consistent, what I mean here is that the channel here and the channel here have to be correlated.
Yeah.
Okay, and maybe some of these statistical models do capture this somehow because they create clusters of reflectors, I think. But some other models don't. So, and we want this to be absolutely true, okay? And one application, for example, is mobility management, right? You cannot just randomly toss a coin and calculate the channel here, and the channel here is uncorrelated, right? But I agree with you. It depends. Some of them are physically consistent. So,
And what about the 3D model? So we still do have to use some ray tracing to train the generative AI?
exactly. Yes, I will talk about this.
Sorry, as you said, we use just distribution, not the fixed answer.
Here.
Yes, is the model Bayesian or not?
It's not necessarily Bayesian, but let me explain this with an example. So, when you use a large language model, right, you ask a question. This large language model, what it does is it predicts the next token with a certain probability. Okay, so if I type the capital of Russia is, the large language model doesn't predict Moscow. It predicts every possible token in the dictionary with a certain probability, and Moscow will probably have a probability of 0.999. And then you sample from that distribution, okay? And then you set this thing, which is the temperature, that tells you how noisy you want your sample to be, how deterministic or how creative. This is something similar here. We have a distribution. Once you give it this, and you give some conditioning variable, it tells you what a distribution of the possible channel, and we sample from that.
So we
Yes.
predict just parameters of distribution.
Yes, and there are different ways of doing it. This is a very good question. Maybe let me expand on this later. If I forget, please ask me again. But yes, it's a great question. There are different ways of doing this. I'll talk about some papers and I'll answer you. Before going into that, there are different architectures for these generative models. Maybe some of you know this better than me. You can use convolutional networks. You can use autoencoders for this. But more recently, people have, focusing a lot on GANs and diffusion models, okay? So these are just different ways, especially for images, for the computer vision community, of creating realizations of something from a distribution. Let's say, probably you all know about this, creating fake pictures of famous people that don't exist, or people that don't exist, okay? So GANs are generative adversarial networks. It's one kind of architecture that does this, but later everybody's talking about diffusion models. It seems these are the state of the art for image generation. So some ideas in wireless have been inspired by this. I'll mention these briefly in a moment. They are more powerful, apparently, but this is basically what we want to do. Imagine that we have measured a few channels. So, and these are, these icons here. But then we want to augment this data sets with fake, synthetic data generation. Okay, and that's what the generative model should do for us. We use the measured channels to train it, and then we wanted to generate channels that don't exist, but that in distribution, they are like the real channels. It's just like the faces of people that don't exist. I show you pictures of real people, and then I want to generate pictures of people that don't exist, but they're plausible. You should fool me. They have to look real. Okay? And one very successful way is this generative adversarial network, which is basically exactly based on the fooling idea. There's a generator and there's a discriminator that should say, this is real, this is fake, and these two have to converge at the same time. Okay, so I have a few slides about some important papers that have worked on this. The slides are dense, and I don't want us, to drown into the details of the slides. So let me just give you hints of each of them. So one way this generative channel modeling has been approached is with GANs, generative adversarial networks. They come in different flavors, but basically, this paper proposes a two-stage approach. It's a paper by colleagues at NYU. So you have two stages. First stage, you want to predict if a certain link is in line of sight or not. 1, 0. Okay. So what is the input? You need to give some input, right? The input could be the location. Okay, I tell you where the user is, and you should tell me if the channel is line of sight or not, for example. Okay. In this paper, they don't give the position. In this paper, they give the relative position between the base station and the user. This has implications. Okay. Anyway, and then once you have this link state, the second stage, which is the more complex one, gives you the full response. Now I come back to your question. What do I generate? In this paper, they generate the paths. So imagine that you are interested in the top 10 paths. Let's say the base station is there, okay? The top 10 paths. It has to tell me for each of these 10 paths, the delay, the attenuation, the 2 angles of departure, the 2 angles of arrival, and maybe I missed one more. I think there's 6 variables. So it generates this. Then from this, I can compute the channel. Okay, the channel impulse response, and so there's a generator and there is a discriminator, which for the Wasserstein GAN is not a discriminator, it's called the critic. Okay, and these two basically they fight against each other until they converge, until this guy generates good enough channels that are fooling the critic, thinking that good and fake they're all equally likely. Okay. It has limitations. It's not spatially consistent because this is based on the base station UE distance. That means that if my distance is whatever from there to here, it's not based on my location. You know, if I had the same distance vector for a different position and different base station, it will not be able to distinguish this. Okay, but anyway. Each of these works is great, but it has limitations. This is actually my paper from an intern, okay? It's a very different approach we took here. Here, we wanted to address the problem of spatial consistency. So we worked on a sequence-to-sequence model here. I give you a sequence of distances, and you should give me the sequence of received powers, okay? And so this just models the power, doesn't model the multipath fading, but it can be good for handover processing. So how does it work? It's similar to the previous architecture. You have this generator, you have this discriminator. I give you a sequence of distances. The generator creates a sequence of received signal strengths. And the discriminator is given the fake ones, the real ones, and it has to decide if they're real or not. There is one extra input, which is the class label. In our case, we have 3 base stations, so we feed the index of the base station. And it had to tell me if the channel is real or not, and also from which base station it's coming from. So you see in the GAN, there is a fight between generator and discriminator. That's why GANs are very unstable to train, because let's say if the discriminator gets too good, the generator doesn't learn anything, and the other way around. And that's why people use diffusion models now. But just to give an idea about things we've done, this work obviously has limitations as well. So one of the latest papers uses diffusion models. This is from the folks at UT Austin. So again, let's not get drawn into the slides, okay? What is a diffusion model? Diffusion model, in this case, is the noise in diffusion model. Basically, it works like this. I give you an image with noise, and the model should remove the noise. Okay? I give you an image with noise, the model learns to remove the noise from the image. So if you train it well enough, in my case, the image is the channel matrix, okay? Just to be clear. So we use the channel matrix as an image. So once this is trained and it learns, it does it through steps. It doesn't do it in one go. Remove some noise, then from the next one, removes a little bit more noise, etc. Once this is trained, you give it pure noise, and it generates some image, okay? So you know that this works very well, again, for image generation, and it seems that it works for channel generation to a certain extent, okay? So I think this is a very good paper. It also has limitations because, first of all, it works at millimeter wave, and millimeter wave channels are more sparse. You know, they have fewer dominant directions. It's probably also easier to learn those. And also, it doesn't generalize because they train this for a certain location. But then if I want to use it somewhere else, I have to retrain the model altogether. So this also has limitations. The model doesn't know anything about the environment. The model just learns, basically it interpolates channels, okay? But again, interesting directions. People are working on this. Oof, okay, we'll cover quite some ground already. This may be to summarize this generative channel modeling. So 3 ways of doing channel modeling: the 3GPP, the ray tracing, the generative models. I pre-train it with some data, and then when it's trained in inference, it generates synthetic data for me, which I can use either to speed up simulations or for synthetic data to train some machine learning models. Okay, that's it. This is just the high-level picture. Yes, please.
A bit of a simple question. Do these models output only power heat maps, or delays, or maybe some error models can be produced?
That's great. They output whatever you want them, whatever you train them for. Okay, and in the 3 papers I have shown, they actually output 3 different things. So first of all, my paper, which is the simplest one, this one outputs power, receive signal strength, power values, dBs. It outputs dB. This one outputs all the paths and which angle they're coming from, and the delays and the power. So from this, you can apply the Doppler and you get your channel impulse response. This one directly outputs the channel frequency response, the H matrix, the channel frequency response. So let's say the OFDM channel. Actually, they reprocess it with some FFT transformation because it's easier for the model to learn in the beam space, in the Fourier transform. So depending on what you need, what you want, you train it for that, it generates that.
Could you clarify the preprocessing stage? So it is stayed not with H, but with directly with the H matrix.
Well, it depends. This paper, what they do is they want the H matrix, okay, the MIMO channel. They want the MIMO channel, but they don't. They do it for millimeter wave, but they don't feed the MIMO channel to the model. First, they do the inverse Fourier transform of this channel, so it gives the beam space. It's the same, but in the beam space, the dominant direction. And then, of course, they do the inverse transform at the end. And it seems that this works better. It's easier for the model to learn this, I think. They must have tried both. But of course, for lower frequencies, for me, it's questionable. Yeah. Also, the diffusion model is important. They have a drawback because they work in steps. They're slower in inference. You cannot generate in one go because you need to go through these denoising steps, and you need to go through multiple steps. If not, they don't perform well. Okay. So.
One more question.
Of course.
So, am I right that this model takes as an input Gaussian noise, and from Gaussian noise it creates the channel? Yeah.
Exactly. When you let's think about the pictures of fake people.
Yeah.
When you train it, you want to use it, so you give it Gaussian noise or noise from a certain distribution, typically Gaussian, and you need to give a conditioning input. That's very important.
Okay.
That's why they call conditioned diffusion models, conditional GAN.
Okay. And what about the physical consistency here? For example, if we have 2 points with correlated channel, but so they has as an input Gaussian noise, is it okay? Can we implement correlated channels create using this model?
Excellent question. So they're supposed to be correlated because the conditioning input X would be very similar because this is the position.
Okay.
At the same time, they are not deterministic because this is non-deterministic and you're feeding random Gaussian noise. Okay. Yeah. So this conditioning input is very important, X. Here they have another conditioning input. This is just the step of the denoising process, but that's not very important. So I don't know how I'm doing with time, but you can stop me anytime. The next part is, so I'm back to the big picture, okay? So let's say that now we have this. We have the digital twin. What do we want to use it for? Two main applications. One, I want to run simulations. Let's say I work on Wi-Fi, okay? So traditionally, you know, if people that work with the upper layers, they like to abstract the physical layer a lot, okay? And that has worked very well for a while. But now with features like coordinated beamforming, these things, if you don't model the physical layer well, what are you simulating, okay? And the other way around. So it's important somehow to run system level simulations that have a good modeling of the lower layers of the radio environment. So now I'm going to zoom in a little bit on this application. How do we simulate? How do we use this in a simulator? How do we use this in a simulator, right? And then a bit more about machine learning model. So again, here, the same tools I mentioned before, the NVIDIA AODT and the Shiona, they do system level simulation for you. What does it mean to do system level simulation? So far, I talked about modeling the channel of one link, but system-wide, to model multiple cells, multiple transmitters, how do they interact with each other, what's the throughput, etc., the interference. So the AODT does this, of course, because it's like a full stack simulator, but it's quite complex. Shiona has, besides the ray tracer, it has a system level simulator tool called SIS, Shiona SIS. This is actually developed by one person. This one guy that develops this, and so basically this is a block diagram. But basically what they do is they have the physical layer abstraction, which is when you send the actual bits and compute the error rates, etc. And then they have a bunch of other things, you know, the power control, the scheduling, the mobility, etc., the link adaptation. So if you use a ray tracer, the ray tracer basically replaces this block, the channel generator. Instead of doing it stochastically, you have it like your digital twin will sit in here. And Shiona SIS allows you to do this quite easily because it's Python code again, and it allows you to do this. But if you want a very complex simulator, maybe this is not enough for you because not all of the features are developed yet. Or maybe you do Wi-Fi, this is different, okay? So I put together this table, which is really subjective, and I try to do this exercise. So I put here the system level simulation engines and the digital twin, the channel generation engine. How easy is it to integrate the channel generation engine in each of these? If I use AODT, it's complex. It has its own ray tracer. It allows you to modify that, but it's a bit complex. Shiona SIS is the easiest, probably, because you can use Shiona ray tracing in this. And if you want to use a generative model instead, you can integrate it in Python. And if you have your own simulator, let's say your lab you have your own simulator, maybe C++, whatever, then there are two different ways of integrating a digital twin. You can pre-compute your channels offline, save them, and then when you run your simulation, you read them. Or then you need to do some integration. You need to do some online channel generation. And there are some papers that, for example, show NS3 and Shiona integration. So this is a developing area in the literature. And the great thing is that people make things open source very often, so we don't have to reinvent the wheel. So that's it. That was about simulation. So now I want to zoom in into this. So let's say that I have certain use cases at the physical layer, and I want to use machine learning for them. I want to do beam prediction, or I want to do channel state information, feedback, estimation, etc. And I want to use a machine learning model. I need data. So here is where my digital twin can give me the data, okay, to do this. I have another ball here which I want to discuss with you, which is instead of giving the data to these models, I can use a foundation model to somehow represent the channel in a smarter way and feed this to the model. A bit of a complicated concept, which I'll try to clarify now. Okay. And this is the last part of the presentation, although there's quite a bit of stuff there. So first of all, what does it mean to do machine learning for deep learning for the physical layer? Why? Here are two examples. CSI feedback. So channel state information feedback. So when you do MIMO, you need to estimate the channel, and this is usually complex or it takes resources, because how do we do that? We send a pilot, the receiver estimates the channel, it feeds it back to us. This takes resources, okay? So this feedback takes resources, and especially in Wi-Fi, this apparently takes a lot of resources. So if you want to scale up the number of antennas, the number of streams, this starts becoming a burden because you need to feed back this channel matrix, and it takes a lot of bits. So people have proposed autoencoders, for example. So instead of giving H, my channel matrix, to the receiver, like compressing and sending it, I encode it with an autoencoder. Basically, I compress it much more. Okay? And I send this, the latent vector. And then the receiver has this decoder. And then it recovers H. So the bits I send here, they are very few, basically. Okay? So they use this autoencoder. So what is this? It's machine learning architecture. Okay, so I need to train. Another example of a use case is this beam prediction I was talking about. How do you do beam alignment at millimeter wave? You basically, because you cannot send a pilot. So before I gave you the example of I send the pilot, you estimate the channel, and you tell me. At millimeter wave, I cannot do this because the attenuation is too much. So if I send you a pilot, it doesn't get to you. I have to beamform already immediately. So for that, the procedure is very different. You do this beam sweeping. So I tried, and this takes time because we need to align beams both on my end and your end. So again, people try to predict the best beam index, maybe based on measurements at a lower frequency. Let's say I know the channel at a lower frequency, and then I try to predict the speed. Okay, so all of these things have been already studied for a few years. They are already, standardized, etc. And these are some of the use cases. There are more. Positioning can be done with machine learning, and blockage prediction, etc. So the traditional solution is that I have a certain use case, I develop a model. I have another use case, another model. Okay, task specific. And also there's a bit of a problem because how do you train this model? Do you train the model at the base station and then you send it to the user? So the base station is made by Nokia and this is made by Xiaomi. Where do you train the model? Does Xiaomi train the model and send it to Nokia, or does Nokia, or do they somehow train it both? So this is a big deal in standardization, okay? So I want to talk about a different way of doing this that is still research, honestly, but I think it's very interesting. And it's to use foundation models. So instead of having task-specific models, can we have a model that is kind of good for everything, and it's task agnostic, and we then can use it for everything? This is like LLMs. LLMs are good at everything. They are foundation models. Once they train them, they can do a lot of things. They can do text summarization, sentiment analysis, things that before needed separate models, right? So can we somehow develop something similar? So we pre-train them to learn some generalized wireless representation, and then maybe we fine-tune them, or we just use them on multiple downstream tasks that in principle are quite different from each other. Okay. Yeah. So maybe let's look at the picture quickly. Imagine this is the digital twin I had from before. This box gives me channels. It gives me the channels of the environment, and I feed these to some. So these are unlabeled data. It's like when you train a large language model, you crawl the internet and you feed it Wikipedia, okay, and everything, okay, and then you can do some self-supervised pre-training. I will talk a bit more about this, okay. So when they train large language models, the data is not labeled. And that's why they can be so big and so good. That's why you can train on trillions of tokens, because they are unlabeled data. I will explain how this is done. And from this, you create a foundation model. So a large language model this way is a model that understands English and maybe understands coding, but it doesn't know specifically how to solve your coding problem. But because it's so good at coding, it can also solve your problem. Okay. So I create a foundation model, and then if I want to fine tune it, then I need some task specific data, maybe specifically for bit prediction or specifically for channel estimation, etc. If I want to, but maybe this box is already good enough. Okay. So how to do this? So I want to clarify my previous point. Through self-supervised pre-training. So this is what has made natural language processing and computer vision step forward, is that I can do self-supervised pre-training. I don't need to label the data. So like when you want to teach a large language model next word prediction, you don't need to label the next word. You already have like a sentence. So you show the first word, you will know what the second word is, and based on what it predicts, you already have the labeled data. So the has to predict capital. The capital has to predict of. The capital of has to predict Russia, right? So this doesn't require human intervention. And it's the same when we have a channel matrix. If I mask some subcarriers or some symbols, it has to predict what's missing. If I mask the channel for an antenna, it has to predict what it's missing. So the data is already there. If this is not clear, I'll spend more time later, but let me continue for the sake of time. So there's a first stage, which is this intensive pre-training by giving a lot of data, but it's unlabeled. So this is cheap. And then if I want, I do fine-tuning. So how do I do the first part? How do I do this pre-training? Two approaches in the literature. One is contrastive learning. So basically, the model has to basically be able to distinguish positive and negative pairs. This is also used in natural language processing. Let's say for sentiment analysis. You show two sentences that are very similar, and you should project them closer in the embedding space. And you show two sentences that are very different, it should project them far apart in the embedding space. And this way, a model learns that king and man are similar, and king and cat are very different. Man and woman are somehow related. A woman and, I don't know, castle, maybe it's unrelated, etc. Okay? Things like this. Contrastive learning. What does that mean for us in wireless? It can be channels from similar close by locations, right? These should be positive pairs. The same channels but masked differently. In one channel I mask one subcarrier, in the other channel I mask another subcarrier. This should be positive pairs, etc. Another approach is reconstructive learning. This is like BERT, the language model. You mask one token, it has to predict the word that is missing. Okay? So it's two different ways: reconstructive learning, contrastive learning. And there are some interesting papers in the literature that do this for wireless. I'm not going to spend another hour on this. And the architectures are different. In some cases, so they all use transformers. Okay. But in some cases, it's only encoder. Some cases, only decoder. Some cases, encoder, decoder. If this feels overwhelming, it's okay. Raise your hand, and I'm happy to clarify questions rather than going through 10 more slides. Okay. And maybe this helps. So my digital twin gives me channels. Let's say these are matrices. Okay, they look like an image. Okay, looks like an image. They are unlabeled, but they are good enough for me because I take each of these and I mask some of the pixels, and the model has to learn to recreate the missing pixels. And I do this many, many times. This way, the model learns what the channel looks like just by reconstructing the pixels that are missing. And this is a pre-trained model. And then, magically, this model is good enough to perform downstream tasks, beam prediction, CSI feedback, etc. Okay, so the picture gets a bit complicated, but let me simplify. It's like this. Now I have trained the model. Okay, I'm here. I trained the model. So now imagine it has some problems, channel estimation, whatever. Here. And these are your machine learning models. For each problem, you have a small model. Normally, you will give the channel to this model, and the model will predict the beam. You give the channel to this model, the model will do the CSI feedback. You give the channel to this model, the model will do localization estimation. Okay, one different. Now, instead of giving the raw channel directly, you pass the channel through this foundation model. The foundation model produces embeddings. Embeddings are high-dimensional representations of your channel, which somehow have extracted the most important feature. When you feed these embeddings, I'll clarify this. When you feed these embeddings, you make the life of this guy easier. Okay, and this guy can be very small model, even just a linear regressor. Okay, and this you train it once only, and then maybe you just need to adapt this. Okay, yes, please.
May I ask a question? What about generalization of the model? Should the model be trained once, and for what generations? Is the trained data set specific, or should we train for every building, for every?
I don't know, but yes, these are the questions. So first question is, should we train again? No, by definition, if we say that this is a foundation model, in theory, without any fine-tuning, this model knows how to extract very representative features from the channel. So what you need to retrain is the downstream model, which is maybe very small. Okay? And your question about site-specific. Excellent question again. The more site-specific it is, the better, but hopefully trained with a lot of data from many different sites, it learns to work for all. And actually, yeah, in one of our papers and other papers also, they train on many scenarios and they show inference on other scenarios, different cities, and it works well because it learns to extract features. But yes, it's an open problem.
But I suppose the trained data set is large.
The trained data set should be large, yes, and it depends on how many parameters this one has as well. Yeah,
on the scale of gigabytes.
The training data set could be like 1 million channel matrices, maybe something like this. Yeah, and these models, maybe 500,000 parameters, something like that. But it's just very early in the wireless community to really know. But yeah, so far. This is probably the first paper, one of the first papers from Arizona State University. For those of you who know a bit about language models, this is like BERT, the language model BERT, where you see this is your channel matrix. First, you break it down into patches. You feed patches. We don't need to go through all the details, but basically, you feed patches and you mask some of these patches. This is the transformer layers, and it has to reconstruct the missing patches. And so you minimize the mean square error loss between the patch you mask and the reconstruct. And you do this through training. It has to reconstruct the missing piece of the puzzle, okay? Once you're done, you throw this away because you don't need any more to reconstruct the missing patch. And you use the model only up to here. So the idea is that at this stage, it has extracted very useful representations of your input so that the final layer could reconstruct the token, the missing patch. Now you don't need it anymore to reconstruct the patch, but what you have here is a very good information extracted from the input, and you can use this for a downstream model. I have another. I know this is confusing. Yeah.
What is the downstream model?
The downstream model is one of these guys.
Ah.
Thanks for the question. Yes. Downstream model. Okay. So this is a generic representation that you feed to your downstream model. It's like a summary. This is a very smart summary of your channel. Okay. So
They analyzed what is the physical meaning of the summary they got.
no, it's really hard. But what they do is they were showing they have in the second version of the paper, because this is multiple layers here. There's multiple layers of transformer encoders. And they were plotting some representations through the different stages. And you see different patterns. This is like in image, in convolutional neural networks, it's like each filter, one filter, you don't design this, it just appears through training that one filter only detects vertical edges in the image, and the other filter only detects round patterns and stuff like this. But it's not by design, it just occurs through training. And sometimes it's hard to interpret what these representations are like. It's hard to observe.
In LLMs, there is an entire field called mechanistic interpretability that studies what exactly those transformer heads or layers attend to. So, for example, there was a cat dimension which attends only to the words related to this cats, humans, tigers.
I have a slide that maybe helps us discuss this. Yeah, it's this one. So, look, let's look at this one. So, what is this? This is a map, and this is a street. Okay, each color corresponds to a beam index of millimeter wave. Okay, that means at this position, the best beam is the one corresponding to this color. And I think here there are 8 beams. I'm not very good with colors, but there's supposed to be 8 different colors. Okay, so if you plot it like this, it looks like this. Now imagine that you take these raw channels, they are matrices, okay, and they are high dimensional, and you project them onto a certain lower dimensional space. You get this. You project them. This projection is called the T-SNE. It's one way of projecting high dimensional vectors. It's not the principal component analysis, but it's something that works very well, okay? This is like in a language model when they show you the projection of the words, and the king and queen, they are close in the space. And man and woman, okay? Same thing here. So if you just take the channels and you project them, they look like this. This is the cloud points. Okay? They look like this. Are they separable? Somehow. If you are a machine learning algorithm, imagine you are a machine learning model, and you need to do beam prediction. What is your task? Your task is, I give you this, and you need to draw decision regions. This is what you need to do. This is a classification problem. I give you a channel, predict the best beam index. It's a classification problem. You need to draw boundaries across between purple, green, etc. So this is if I give you the raw channels. Instead of the raw channels, I pass the raw channels, I generate these embeddings, and I give you these embeddings. Now let's see what these look like. They look like this. Okay, this is, if you further do some fine tuning, even better. You see how your life is easier as a classifier. You have to tell me the beam index. You have to just draw these separation regions. It's so much easier. So this is what they mean when they say the downstream model can be simpler. The foundation model was not trained on beam prediction. It was trained on just channel mask reconstruction, but it can help a downstream model do their task. Yes.
Next question. As I understand, the channel task agnostic channel representation in subway compresses in the embedded space, the channel.
Good question. Not necessarily. There's an excellent question. You are asking, this occupies a certain space, whatever, 32 by 16 dimensions, but what about the embeddings? It depends. It can be even in the same dimension.
So
They're just better organized.
am I correct that the gain lies in separation.
Yes, in this case, yes, but you could design it in a way that the embeddings occupy less space or more space.
But as for less space, I suppose it is bound by variability of the channel.
Sure, the entropy of your data. Yes, this is a very good point, actually. Yeah. And maybe it's easier to look at it from the line of sight versus no line of sight. The raw channels, you see this color is line of sight, maybe, and the blue is no line of sight. If you plot them, they are a bit mixed, but when you plot the embeddings, they're very easy to separate. Okay? So, I don't know if we have a little more. Okay. So this is another way of tackling the problem. This is my paper with some collaborators. It uses a different approach. So this uses what's called the masked autoencoder. What is that? So for computer vision, you have an image, you mask it, you only have some visible patches. You give these visible patches to an encoder. Okay? This is a transformer, many transformer layers. The encoder creates some embeddings of this, represents the visible patches, and you give this to a decoder. The decoder has to reconstruct the whole image just from the visible patches. See, very intuitive concept from computer vision. So can we do this for wireless channels, right? And notice, we don't want to do this for wireless channels but only because we want to reconstruct a wireless channel. We want to do this because when this works, when you train the encoder and the decoder, the information you have at this point is very good. The encoder was able to summarize the visible patches in a way so that the decoder could reconstruct the rest. And notice how the decoder is smaller than the encoder. That means the encoder has to do a very good job so that a stupid decoder can reconstruct the whole image from very few visible patches. And the more you mask, I will talk about this, the more you mask, the better, because it's harder for the encoder and it needs to learn a very good way of representing the visible patches. Okay? Of course, if you give 90% of the patches, it's going to reconstruct very well in training. But that's not what you want, because that means the task was too easy and maybe these representations are not really good. You wanted to train with a difficult task. So yeah, don't worry about this. Just to say that this works as I said before, the mascot encoder. You have your raw channel. In this case, the channel is number of antennas by number of subcarriers. You do some pre-processing, the usual thing. You extract patches, whatever, and then you mask some of these patches. You mask. So you only have few visible patches. How many? It's a hyperparameter. I will discuss in a moment. Then again, you do some pre-processing because in our case, we have real imaginary parts. The channels are complex, okay? And then you send this to the encoder, okay? So this was the pre-processing one. So this is the encoder. You receive this pre-processing. So the encoder has to do the tough, heavy lifting, creating some representations, okay? It's multiple transformers here, okay? You have multiple transformers. Now, then we have the decoder. Let me very quickly go to the decoder. And this is the decoder. From the visible patches, the decoder has to reconstruct the image, okay? And you train it, and this, then when it converges, you disconnect the decoder, you don't use it anymore. All you need is this information here, the embeddings, okay? We did something extra. Instead of just doing this reconstruction loss, we train it with some contrastive loss. So contrastive loss means I give you two channels that are similar, and you need to project their embeddings near in the embedding space. Okay, we do this in some way that I think it's cool, but we don't have the time for all the details unless you're interested. So basically there are two losses here in the training. One loss is the reconstructive loss, which is a mean square error. You know, the real pixel was this, you predicted something else, was the mean square error, feedback the gradient. And the other one is contrastive loss. I give you maybe one channel and one augmented version of the same channel. You need to project them closer in the space. Or I give you two channels that have nothing to do with each other. You need to project them far apart in the space. Anyways, so here's what happens. When you train it, now you want to use it. Okay? Inference, you want to use it. So this is your downstream models, okay, for each of your use cases. Instead of giving the channel directly to the model, you pass the channel through the autoencoder, you give the embeddings that it has learned, and you make the life of this guy easier. Okay? Same concept as before. Because these embeddings make the life of this AI model easier. And they are task agnostic, meaning they should be helpful whatever you want to do downstream with them. Okay? So similar concept. Now I have a bunch of plots that I don't necessarily want to go through. This is basically the mask reconstruction. You know, you have the full channel, you mask some, and it has to reconstruct. These are examples for the magnitude and the phase. Okay? And maybe one more thing, just one more thing. This is the performance. This is like the top one accuracy. Basically, this is for beam prediction. How often it predicts the correct best beam, okay? And this is plotted versus the masking ratio. When you train it, you mask a percentage of the channel, okay? And you see that there is an optimum sweet spot. So it's not good to mask too much because maybe it really struggles to train, but it's not good to mask too little because it's too easy to reconstruct in training. It doesn't learn enough. And in these experiments, say 0.6 was optimal. It's just to say that this is a critical hyperparameter. And there's a bunch of other plots we don't necessarily see. And this is basically comparing to state-of-the-art approaches that, of course, it does better. But more importantly, what does it mean that it does better? Not only it performs well, but it performs well with less data. So, for example, we plotted versus the training budget. Okay, imagine that you want to train this one. When you train through the embeddings, it learns very fast with fewer samples. This training, not only this model can be smaller, but also it learns faster with less data. So, you know, bunch of tools. And that's, I just want to recap. Okay, well, this is the last slide. So, what did we talk about? Wireless digital twins as emerging tools to design, to optimize wireless networks, to evaluate them. Site-specific is good, especially for machine learning applications. We want data that represents where we're going to deploy our model because we want to capture the propagation features of the real environment. It's hard to build these digital twins, but there are new enablers. We have discussed new ray tracing tools that are good for us, especially in research, and generative AI ideas. Once we've created these digital twins, they can be very useful. One way is if we want to do realistic simulations, we want to evaluate systems with site-specific data. And the other one is when we use machine learning and we need data for model training, they can be very useful to generate synthetic data for model training. And we also discussed using the channels as they are or passing them through some foundation models that do a task agnostic representation and then, you know, feeding this to maybe simpler downstream models. Thanks for, you know, following me with this. Yeah, I know it was a bit dense. I hope.
Very much.
Questions? Thanks. Question. Concerning task agnostic representation, as I asked, the metric is MSCI for reconstruction in some architectures.
Yes, yeah. For reconstruction, it's typically MSCI.
My understanding is that for some minor channel tasks, like you may reconstruct matrix not perfectly, but maybe reconstruct matrix multiplied by some integer matrix. It won't change the subspace, so SNRs after precoding will be the same. That nuance is not captured by MSCI metric, I understand. Are there any research direction?
Very interesting question. I don't know how to answer this question, but I can answer something related to that. Okay, but you're right. For example, in this paper, remember we discussed the diffusion model paper. Okay, it's for channel generation. It's not for foundation models, but it's related. So in this paper, how do they know if the synthetic channel is good or not? How do you know if the synthetic channel at this location, so let's say I have these real measurements and I want to generate the fake channel at this location? How do I know if it's good or not? So imagine you have the ground truth. What do? You compare the synthetic channel to the real channel? You do the MSC? No, you cannot do the MSC. Why? Because imagine that the diffusion model creates exactly the same channel, just phase rotated. If you do the MSC, it's going to be huge. But that doesn't mean the channel is bad. The channel was very realistic, just phase rotated. So in this case, they don't use the MSC. They look at the beam space and they compare the main direction, how far apart the main beam of the channel is from the beam. There are some good plots. Of course, I didn't want to crowd this, but I agree with you. It's a very good point. Yeah. Thank you. Yeah.
First of all, thanks a lot for the presentation, extremely interesting. And from my side, maybe from this side of site-specific simulations, let's say we want to run a lot of such simulations to the model scheduling or maybe application features and so on. And then the main issue here is the complexity of such models, because even if we now use some statistical models from GPT, with Quadriga or chemistry, then complexity can be an extreme issue. For example, if we working with a lot of antennas, maybe or users. So my question is, would you comment on the particular numbers of VRAM, runtime, maybe? Because we are engineers or maybe researchers from the engineering side, so the complexity is a major topic for us.
Very good point. So let me understand a bit better. So what kind of simulations do you run? Is it like
let's say
cellular or?
Let's say it may be cellular, it may be one network, I mean Wi-Fi.
Okay. Let's consider a cell with, say, 40 users.
A cell with 40 users.
Yeah.
Let's say the GNB
64 antennas.
Yeah. And users have 1 antennas.
Yeah, it's as basic as GPT settings.
40 users. Okay. Question is, can you pre-compute these? Or they need to run on the fly. It's not real time, of course, right? It's not real time. It's not real time, so that's a good thing.
But the question is how many time we need to recompute and how many spaces or resources.
To pre-compute is a problem if you, for example, have mobility. That is a problem. In your case, pre-computing or no pre-computing doesn't make a difference because it's offline simulation. So let's say you drop your users. Okay, you drop 40 users at a time. You need the channels of all those users. Okay, if you use Shiona, So one good thing is that the number of antennas is not a problem for you. Why? Because the ray tracer doesn't need to calculate the paths to each antenna. It can do it to one antenna, and the rest can be post-processing calculated because it's just a post-processing. You know, you have the plane wave approximation. So once you know the signal received at this antenna, you just do your phase rotation and you have the whole. You post-process for each path. That's why here I say only, so this means only if you are in the near field where there's a curvature effect of the array and you cannot use the plane wave approximation, it's not your case. So with the plane wave approximation, that should not be a problem. You have 64 antennas, that should not be a problem. So you can run the ray tracer, and then if you also question is, you run on GPU or CPU? There's a question. If you run on CPU, maybe it's slow, but it will run. You have enough RAM.
Light is high or light assume GPU, but how many time it will run?
If you run on GPU, I think the runtime is pretty good. What you need to do is, depending on your RAM size, you choose these numbers, right? You just try. You can see when it creates this tensor, how big it is. Basically, this tensor, the size is going to be the product of these variables, right? Because it's a high-dimensional tensor. So you see how many gigabytes it occupies, and you cap it so that it fits in your RAM, right? So, for example, let's say that you want 40 users, but you can only fit 4 users, right? Because otherwise, this tensor becomes too big. So you run the ray tracer for 4 users, and then that tensor, you pass it to CPU. And then you run the ray tracer again for 4, you use a for loop. So you run the ray tracer on GPU, it's accelerated, only for 4 users, and then you copy the tensor to CPU. Of course, it's slower, but you can do that. The GPU part is fast, and the rest of your simulation runs on CPU with the channels generated from GPU. I don't know if I'm explaining myself.
Could you give some exact examples? For example, how much time do we need to generate such model? Like, okay, if you want to have a trace of, say, 1 hour, we need to spend 1 day of computer time or 1 minute of computer time.
Okay, this is a difficult question. So I know about the trace of 1 hour, but these snapshots that you mentioned, 40 users, so 40 locations, this should run in seconds.
For how long time?
If it fits on the GPU, it runs in seconds.
For 1 location, several seconds?
Yes.
Yes, maybe you've used it, you can comment, but yeah.
Yes, I have used the CERN on series ago, and the typical scenario for Wi-Fi takes about 2 seconds.
On CPU.
Yes, but it uses GCAM power, and I have many cores, so it automatically parallelizes.
Right. So on GPU, you can probably do 10 times as much in the same time.
Yes.
Yeah, especially with the new version of Xion. Then going back to your question, if you have mobility, for example, so something interesting that they introduced is tricky, but so in theory, if you move the user, you should rerun the ray tracer completely for the new position. But they have something called the Xion mobility thing, where if you move the user a little bit, it doesn't rerun the ray tracer. It only applies the Doppler effect, accounting for the small movement. And then only after it has moved enough so that the macro features of the environment have changed a lot, then it reruns the ray tracer. So this saves also a bit if you're doing mobility. Yeah.
Actually, the GPT models also do that. They are spatially consistent in terms of Gaussian spatial processes.
Yes, yeah. But it's just not site specific.
Yeah.
I think one question that I would expect from those working on Wi-Fi is whether this works indoor. Nobody asked me that question. So that's good. Yeah. So it works indoor, but there's a catch, because modeling the indoor environment is trickier, right? There is more small details, and this is something that I think is still a bit of a limitation. Or outdoor to indoor. Let's say, you know, we want to study 6 gigahertz to see if it should be Wi-Fi, it should be cellular, the interference. To model, let's say, outdoor to indoor propagation, the ray tracer is very sensitive to that, and we probably need measurements for that. So this is, I see this better for cellular.
But probably we can still find soon some sensible models from balls or some wooden parts and aggregate it as a statistical model.
Probably you can, once you generate the channel, you can add this on top. Maybe you can add some attenuation. Yes. They do have refraction now, penetration in the new version. But again, the modeling indoor is complicated.
Any other questions?
So this is a general question. Using AI and machine learning in research creates kind of a split in the research community. So one group of researchers say that this is the future, and we can see that in the topics for new 5G releases and towards the 6G networks. And the other group says that AI models can be unpredictable, and that's why they favor 3GPP models, because they are simple and but predictable. So what do you think? Do these AI models have a chance of taking the lead in the possible implementations of algorithms, channel models?
It's an excellent question. I think for some use cases they do, and these use cases are already basically there is work in the 3GPP for these use cases. For beam prediction, for channel estimation, even for localization. But this kind of use cases they do have. Especially I hear for localization and non-line of sight, it really works much better than off-the-shelf algorithms. Is it good for everything? Maybe not. Maybe it's an overkill, but it's good. For channel modeling, I think it's particularly helpful, because channel modeling inherently is really complex, and it's really hard to model a site-specific model. So I think their machine learning can help. For these use cases, I believe in it, but not for everything. Some people have, are working on, let's say, scheduling, maybe higher layers, reinforcement learning. I cannot comment. I'm a bit skeptical, but maybe there as well, there can be gains.
Okay.
And maybe, sorry, some say that it's not just about the gain. Let's say that the model gives you a 5% gain. That doesn't justify. But sometimes it could be to be future-proof. Maybe you change your development from traditional algorithms to machine learning. And maybe this is future-proof, meaning that any further changes down the line are easier to implement because you just feed new data and the model learns. So maybe it's 5% now, but it could be more in the future, let's say, or you have more flexibility in the future.
Yeah. And well, perhaps my question a little bit continues the question of the previous video. And the question is, here and often in papers, I see these two tracks, the AI-based generative AI and the ray tracing, as sort of parallel or even one opposed to another. But for example, in modern NVIDIA DLSS technology, DLSS 4.0, they claim that they first use a very simple and cheap, small, reduced level of details ray tracing, which is then augmented by the, as we know, the diffusion models can in-paint, starting from a very rough sketch, not just Gaussian loss. They can in-paint, and perhaps by this they can converge in small number of iterations and have grounding or temporal consistency. So are there research that combine the ray tracing and AI technologies in one step?
Yes, there are. I didn't want to put them in this presentation because it will be 2 hours. There's one very interesting paper by Meta and Arizona State University. So So in that paper, basically, and then I'll be fast. I didn't talk about level 4. For me, that paper is a bit related to level 4. So what you need here is some real-time ray tracing, but ray tracing real-time is very hard to do. So this is what they do. They run some ray tracer only for the geometry. They only want the paths from the ray tracer. They don't want to calculate any electromagnetic effects, no absorption, nothing, just the geometry. And then they feed this to machine learning models. The machine learning models are supposed to learn the electromagnetic properties and the interactions. And these are trained with measurements, okay? And this is like the combo maybe that you're referring to. So they learn the environment. So basically it's a neural ray tracing. And they had some very interesting plots. They show that it works, and probably it's faster than the ray tracing one train. But still, 3GPP is very far from that, you know?
Thank you very much.
Another question?
Maybe one more. I am interested in your vision about tools and emitters. I mean, that GPT or 802.11 have a chance to incorporate such models. I mean, level 3 or level 4 is a new evolution.
The short answer is NVIDIA also participates to the 3GPP. I know the delegate, so they're obviously pushing for this.
Yeah,
right.
But at the same time, from 1.5 is still using models from 2014, I guess, 11AX, I guess, you know.
Yeah.
So the knowledge GPT models, you know, under the committee activities.
Maybe, I don't know if this is going to be an unpopular statement, but maybe Wi-Fi will follow what 3GPP does.
Wi-Fi has recently established a group of channel model to relate to yeah, something happened there.
Yeah. So in 3GPP is still here. But that doesn't mean the companies don't use level 3. That means that when they do their simulations and they present the results and they compare to benchmark it, it's much easier to benchmark with level 2 because you have the statistical model and you benchmark. But internally, we also use site-specific things. So from the standardization point of view, it's about unifying the benchmarking. And how do you unify? You know, one company uses one ray tracer, another company uses another ray tracer. That's why I think the generative models can be very useful, because then we agree that we should use the generative channel model. Everybody uses it, and we benchmark. So maybe this can help, because it's going to be really hard to say everybody should use this ray tracer. You know, who can decide this? All companies have to use this ray tracer, but maybe an AI model shared by all companies to benchmark, that could be the first way. And then 802.11, maybe a bit after that. They are understaffed, you know, so give them a break.
Other questions? Okay, let's thank again.
Thank you.